In this video I'm going to show you how to write and to read from EEPROM, how to write data to EEPROM and how to read data from EEPROM, and I'm going to specify the address in the EEPROM. So first of all, let's just go and quickly have a look at where do we find EEPROM. EEPROM, as the name suggests, is electrically erasable programmable read-only memory, and it's a certain type of memory sitting inside your microcontroller. In the specific AtMega328P, if I can just get to this other slide, you will see this is let's just get to this one. It has 1024 bytes of EEPROM, which is 1K. This is the AtMega that I am working with. And it says here EEPROM is a place to store data. It is not deleted when power is switched off. So this is what's nice about EEPROM. It actually keeps the data permanently. If you do not remove it, it will stay there, well, for as long as possible. The disadvantage of EEPROM is that you cannot overwrite it more than, I believe it's something about 10,000 times. And it sounds a lot, but it's quite easy to destroy it within seconds if you don't do it properly. So EEPROM is very nice. It is, as it says there, it keeps the data inside the specific memory. And something like, let's say you've got settings. Let's say you've developed something and you say, let us assume that the maximum current can be 10 amps in an electric motor. That's a setting, that 10 amps. So you can then go and change it in EEPROM. You can get that data from EEPROM, and if you want to make maybe the setting 8 amps or 12 amps or whatever you want to change, that is the place to store it. So it's something that is changeable. It is possible to change it, but normally once you've changed it, you will keep it for a while. I mean, if you, for instance, think about running hours of a motor, that is something that must be updated, and when the power shuts down, that data should be kept. So that is why we will use EEPROM. Now in EEPROM we have got three distinctive registers associated with EEPROM. The first one here, it says it's EEA, RH and RL. So what this is actually the address registers, low and high. So this address register, let me just see, this address register, as you can see here, it contains basically the 8 bits in the low register part and 2 bits in the upper high register part, which is 10 registers. 2 to the power 10 is 1024. This is the number of locations, positions sitting inside EEPROM. That's why it's got 10 bits here. Other AVR microcontrollers maybe have got 14 or so, and it has got bigger space to store EEPROM in. So as it says here, these two registers will then basically refer to a specific position inside your EEPROM. So this will dedicate and say this is the register that we're talking about. So if you can place values in here, it will direct you to that specific position. So that is the address registers. The next one is the data register, the EEPROM data register. It says this is the one sitting here, EEDR. So if, as you can see, these arrows are basically pointing inwards and outwards. So if I want to write data into this EEPROM, I will place it in EEDR, and it will be written into the location specified by the address. If I want to, if it's already written somewhere and I can specify the address, I can read the data from the from the EEPROM to EE address, and that's what I will collect it. So this is why it's got inwards and outwards arrows here. And then the last one is actually this one, which is called the EECR, and that's the control register. Now the control register, as you can see, consists basically only of 4 bits. Now I'm not going to talk about this one at this stage, which is the interrupt enable register, so because we haven't done interrupts yet. So the bit number 3, I'm not going to talk about that one. If we look at this bit 0 and bit 1, the 1 is it's EE write enable. So if I want to write to the device, to the EEPROM, I will make this bit a 1. If I want to read from the device, I will then make this bit a 1. So it's quite logic then that you cannot have a 1 here and a 1 here, because if then you tell the device I want to write from I want to write to you and I also want to read from you, which is ridiculous. You can't do that. These two values here must be opposite values. If this one is a 1, that one will be a 0. If this one is a 0, that one will be a 1. Both of them can be zeros. That just means you don't want to write, you don't want to read. That is fine, but you cannot have both of them 1 and 1. So these two must be, as I've said, if the one is a 1, the other one must be a 0, definitely. Then again, bit number 1 and bit number 2, this MWE, this is the master write enable, and the write enable works together. So if I want to write data, I must take this master write enable bit and make it 1, and within 4 clock pulses I must also then write the data, also write the data by making this bit a 1. So if this is a 1, normally directly after that you will make this one a 1, because what happens is if you make this master write enable a 1, 4 clock pulses later this one will in any case return back to a 0, and this is also where you can check to make sure that your write enable or your write has been completed. So make this a 1, the master write enable. Directly after that you do make this one a 1 if you want to write data into the EEPROM, and automatically it will return back to 0. And we are also going to wait. It's easy to wait for this specific bit to make sure that it is a 0, because only then can you carry on with your program. So what I'm going to do is I'm first of all going to show you how to write data into before this slide here says what must you do to read from EEPROM. I'm not going to do that. Now I first want to write data. Let me just get there. Yeah, this is how to write to EEPROM. And if I can show you what I've done in my case here, I have set up something like this, where I've said, let us set up PB5 as an output pin. It's just, again, I'm making use of the Arduino. So PB5 is connected already to an LED on the Arduino board, although I write my programs in Atmel Studio. And then I've also set here set up port C, specifically PC 0 to 5, so it's 6 bits only as inputs, and also activate the internal pull-up resistors. And then I've set write the value, the data of hex 28, and I've specified the address. So in that EEARH and RL, this is what will be placed in that specific address 5F. And I've also, very important, I've said here, do this outside your while one loop, because if you do this inside your while one loop, you are going to write data to this thing continuously and destroy that data position, which is address 5F. And this is why I've said that. You will also see in my program that I've written this outside the while one loop. Very important, this point here. Now I say you must now read the data being placed on port C and compare this data. It's actually not date, it's actually data. Compare this data in address 5F hex in EEPROM. So we're going to go to port C, have a look at what is sitting there, and then compare the data sitting in 5F. We know in 5F, I've already said we've programmed in there hex 28. So now we are going to, as soon as it's hex 28, in this position, I have said then if the EEPROM data and port D data are the same, you must switch on the LED PB5. Otherwise, switch it off. So I've got the circuit diagram here, but at the same time, I've also got the design with me, which is this one here. So yeah, so I am gonna take this hex file from my Arduino Studio, and I'm gonna program this specific Proteus design of mine. And as you can see here, I've got from PC 0 connected up to PC 5, and only switches being connected here because I've activated the internal pull-up resistances, and PB5 is actually connected to this LED sitting here. So let's go to the program, And first of all, it says here, wait, you must actually wait until EEWE becomes 0. So if I go to the program that I've written here, it's this one here. So the first thing I do, again, like in all programs, you must include the io.h, the input-output header file. And because I'm working with EEPROM, there must be an EEPROM header file. Now, for some reason, maybe this is an older version, I'm not sure, in that EECR, the control register, they did not define EEWE as a 1, and this is why I've done it here, and I've also defined EE master write enable as a 2, because that refers to the bit numbers. And then I've also just defined here 2 chars, which is the one I call compare E. That's actually the value being in the EEPROM, and compare P is the value sitting on the port, on port C it will be. So if I look further in my program, what I've done here, in this line here, what I've done is just to make PB5 and 1, which is an output. In other words, PB5 is an output. And what I've done here is I've actually made DDR-C a hex value of C0. So C is actually 1100. That means that bits 0 to 5, as I've said, is actually all zeros, meaning they are all inputs. So PC0 to PC5 are all input pins. So I've set up the port direction. And we know by now, if you directly after you set up the port direction, if you go and write port C with 1s, and as you can see again, I've written 3F here, meaning bit 6 and 7. But 6 and 7 will be zeros, although they're not there. One of them, it's not there, but if you write 3, it is 1 1, and F will be 4 1s, meaning I'm activating, in actual fact, the pull-up resistances on PC0 up to PC5. That is what I'm doing with this specific line here. And here I'm just making sure I know that PB5 is an output, so I'm just switching off that LED. So it says here, this section writes data to the EEPROM at this address of 5F. So the very first thing, if I go back to this one again, it says wait until EEWE becomes 0, and this is what I'm doing. This is what I'm doing in my program. So here I say while, and as you can see here, I know that EEWE, I've defined it just before. Here it is as bit number 1. So I'm checking this specific bit and I'm testing it by ANDing it together. So if this bit is a 1, it means it hasn't been completed a previous writing exercise. So if it's a 1, you will just wait here. But as soon as this write enable line goes low, normally it will be a low, but we always check for that. As soon as it goes low, you will skip this statement here and go and place into EEAR. As you can see here, it's just specified here as EEAR, the value of hex 5F. I could have said, because 5F can actually fit in 1 byte, I could have said EEAR L for low. I could have loaded this also in here. By using EEAR, I'm just actually specifying that the high byte will all be zeros. Okay, so here we've specified, we need to specify the address. So if I just go again to, it says here, write your new EEPROM address to EEAR. This optional, I'll explain later on what this means. It's not optional the way I'm doing it at this stage. But yes, step number 2, that was done. Okay, the next one is write your new EEPROM data into the data register. Again, it says optional. That's not so. Not for the way I'm doing it at this stage. These slides are from a different place, but I'm making use of these slides just to make sure I'm sticking with a specific book. Okay, so I need to write the data into the data register. So let's see what happens here. And I've said I'm going to write
28 hex, which is what I've done here, into EEDR, the data register. So 28 was placed in there. Then, as I've said, what you must do if you want to write the data, you must make the master write enabler 1. And this is exactly, I'm ORing this specific bit in the control register with a 1, meaning the bit MWE will be made a 1. And this is what I've done here. Directly after that, as I've said, you must, within 4 clock cycles, you must also make WE, the write enable, a high. And this is what is done with this statement. So those two, as I've said, must always be close to each other, preferably the one after the other. So now it's written, but while it's writing, it takes a while to write. We are again going to test for that write enable pin. And if it's high, it means it's still busy writing. So this is why we will wait here. And as soon as this bit goes high, if this bit goes low, this statement, we will skip the statement and go to the next line. So this section here has now written the data of hex 28, that hex 28, into this address 5F. But again, as you can see, where's my while 1? Here it is. It only starts here. So I've written all this data. I've written all of this before the while 1 loop to make sure that I only do it once, because if I do it in the while 1 loop, it's going to destroy that memory very, very quickly. Good. So let's just go back to just to this one. It says here, set the master write enable bit to a 1. This is exactly what I've done. And within 4 clock cycles after setting that one to a 1, you must also set the write enable to a 1, which is also exactly what I have done. So writing into EEPROM, I've completed all these steps as I've said already. Come on. Yeah, so here everything was done. So now let's go back to this one and let's see, how do we read from EEPROM? Again, we will always test this EE write enable bit to make sure that it is a 0. You must wait until it becomes a 0. So let's go back to the program now. And now we're sitting in the while 1 loop. So in this first statement, I'm just testing again this write enable bit to make sure if it's still a 1, it means it's still writing. That's basically what it means. In my program, as I've written it, it's not really possible, because I make sure here that it gets to be a 0 and then I carry on. But it's no harm done if you just check that bit again. So I'm checking, in this case, if the bit is still a 1, I'll wait, but as soon as it goes to 0, and I will carry on with the program. So again, wait until the write enable bit becomes 0. So that one, bit number 1, was done. Write your new EEPROM address into EEAR. So you want to tell this device, where do you want to read from? So in the program, in my case, I will say I want to read from address 5F. So that's the address. Again, I could have just said EEARL. It would have also worked, but then I should have also said EEARH must be 00 hex. Then I'm sure I can't go wrong. But yeah, nothing prevents you from just using this name, which is the combination of the low and the high address register. The next line is this one here, where it says, now I want to read the data. So if I want to read the data, again, we've checked, we're now sure that this write enable is a 0. As I've said, they should be, as soon as it comes out, yeah, I know this is a 0. And now I can change this one to a 1, so they're opposite. So that is fine. So in this specific case, I write a 1 to EERE sitting in the control register of EEPROM. And by writing a 1 to it, I say basically I want to read the data. And where do I want to read it from? Well, I've given the address where I want to read it from. So the data will be fetched from this address. It will be read, in other words. That's what we do here. It will be read from this address, and it will be placed into EEDR. Now we know that the data in position 5F hex is hex 28 because I've programmed that in there. But now I'm transferring that value into this variable by the name of compare E. So in compare E contains what sits inside the EEPROM. Now in the next line, what I'm doing here is I am reading what sits on port C. Now port C, if you remember, we made port C as an input port. The whole, basically almost the whole port, we made that as an input port. And as soon if it's an input port, I can only read the data on pin C, and this is what I'm doing here. I'm reading the data on pin C. But what I'm also doing is I'm ANDing that value with hex 3F. The reason for doing that is, if I do this, I'm basically making sure, because if you look at 3F, if 3F is, if I can type it here, it's actually 00111111. So if I take this value and I AND it with pin C, I am making sure that the bit number 6 and 7 will definitely be zeros. That's what I'm doing. I'm not forcing the rest of the bits to be ones. They stay as they are, but bit 6 and 7 will be forced to become zeros, and this is why I'm doing it. I know, in other words, it can stay only from a maximum. The input on port C can only be a maximum from 0 hex up to 3F. That's the maximum that can be sitting on port C. But this is how I get rid of the bit 6 and 7. And now I'm just comparing the two values. I say if the value that I basically collected from EEPROM is equal to the value that I'm collecting from the port, then you should switch on the LED. Otherwise, switch off the LED. Yes, and if I now go to my Proteus design, which is this one here, let me just quickly, before I do anything else, let me build this. Let me build this thing. There it is, build succeed. And then I'm just going to program the correct hex file in my Proteus design. Let me just get to, I think I did it on my desktop, temporary files. Yeah, it should be in here. And if I program that, just make sure it looks like it's the right one, and let it run. At this stage, let me just close everything. At this stage, you see basically all zeros. If I open this, this is a 1 sitting on PC0, so the hex value is in actual fact 00 here and 0001, so it's 01. And you'll see that the LED is off. And I can change these inputs on the port C, and you will see that nothing happens. It will only switch on if the value on port C is hex 28. So these two, if I make this a 1, that is the 2. That's where I get the 10. This is where the 2 comes from. And this 4 lower bits, if I make this one a 1, you'll see now I'm sitting at a value of 2, 8 hex, and that's where the LED switches on. Any other combination, let me just open this one here, it will switch off, because now I'm sitting actually with a value of 2, 9 hex, which is not 2, 8, and the LED is off, so they are not the same. So whenever it's 28 hex, I can it will then definitely be switching on the LED, because the comparison, it compares the two are exactly the same. And this is how you do EEPROM writing and reading when you do making use of this. You specify the hex address of where the data must be placed and where it must be read from. In a follow-up video, I'm going to show you how it is also possible to make use of a header file, and then you don't use the addresses, the compiler will actually decide where the value will be placed in if you assign a name to it. So I'm going to discuss that in the next video. Thank you.